Okay, so we're essentially finished with the quasi-local horizons in equilibrium. So that was a topic that we've been doing. So and we saw that there are several notions that we introduced. First was that of non-expanding horizon. So this is a three-manifold, which is null, so null three-manifold, such that the expansion of its null normal is 0. And we saw that if the expansion of one null normal is 0, then if you rescale the null normal by function, that expansion is still 0. And this is surprising that, again, this is sort of a very nice example of the interplay between geometry and physics. The surprising thing is that this at first looks like it's just one condition, but it has a whole bunch of consequences which are very rich. And what we found was that, in fact, that delta from space-time and the metric in space-time, delta inherits surprisingly structure due to interplay between physics and geometry. And in particular, we saw that because of we use physics here, that is to say we use Einstein's equations with a dominant energy condition, and that so Einstein's equations, this is a dominant energy condition. This implies immediately that in fact the shear is also 0. We just began with expansion is equal to 0, and it also says that TAB and LB equal to 0, where this hat means at points of delta these equalities hold, and the shear equal to 0 and the expansion equal to 0 together, then that told us that Liel of the metric is equal to 0, where the QAB is a metric of signature 0 plus plus, and that is just the pullback of the metric. And it also told us that in fact that we can pull back grad A, and this grad A, which is defined to be dA, this is a torsion-free derivative operator. On delta, such that dF to dC equal to 0. We saw this, I outlined the main steps of this, and this homework which is due on not this Wednesday, but a week from this Wednesday, February 28th. This is one of the problems that you will have to do in some detail. I apologize that I could not hand back your graded homeworks today. Because of this NSF panel, I have not been able to do very much between last Wednesday and Sunday night. And so I'll try to do it as soon as I can. Okay. So this in particular told us a certain notion of equilibrium. Namely, it tells us that the intrinsic geometry is time independent. L is a null normal, so L defines the notion of time, if you like, and it is telling us that the intrinsic geometry is time independent up here. So this is the interplay that I was talking about, that we first use physics, Einstein's equations with energy condition. That tells us that sigma equal to 0, and then there is no flux of energy, matter energy falling across, and that told us then that the horizon is in equilibrium, and then we also had this D. And we also learned that dALB is in fact equal to, there is one form omega such that GALB is equal to this. These are all on the horizon. I will not always put hats because we're mostly talking about on the horizon. So this is what we saw last time. And then the statement was that this was the first notion, then we have the second notion, which is weakly isolated horizon. So is delta is a non-expanding horizon. But we choose some family of null normals. Here we got these null normals, LA and L tilde A, which is just equal to some function on the horizon times LA. So this is an arbitrary function of the horizon times LA. This is null normal. So if I want to write it explicitly, it's a function of three variables: V, the affine parameter along L, and the angles theta and phi times LA. So I can just this is allowed family of null normals. I can always rescale it so long as f is positive, so that L is still remains feature directed. And then we got weakly isolated horizon. And then what we do is, from this rich family of null normals, you can always choose a null normal. So so a weakly isolated horizon is a non-expanding horizon together with a choice of null normals. So it's a subclass now we're selecting from here, and where here the freedom was that of rescaling by arbitrary function, and now the freedom is just rescaling by constant. So we're given an equivalence class, which is one null normal up to constant rescaling, such that VL of omega equals 0. So of course, because the non-expanding horizon, VL of the geometry is equal to 0, but now we are asking that one of the connection coefficients, part of the connection is also in equilibrium, is also time independent. And this is the same as i.e. LL of dA minus dA of LL. So LL, the action of dA on LB, the action of G on LB is lead drag by L. So this is another notion of equilibrium. So this is a stronger notion of equilibrium. And last time after the class, Shorab asked me, what is the difference between the non-expanding horizons and weakly isolated horizons? What is it that we have changed? What is it that we're requiring more? Well, what we're requiring more is, of course, that LL of omega equal to 0. But this just says that if I choose an arbitrary arbitrary null normal in the non-expanding horizon with this freedom up here, then this condition will not be satisfied. But if you give me a non-expanding horizon, where I've got a rich family of null normals, and you can show, and this is another homework problem, that you can always choose a null normal such that this condition is satisfied. So all we are doing is, really we are giving this non-expanding horizon with a rich family of null normals, and all we are doing is, we are selecting from it some subfamily, much smaller subfamily, which satisfies this condition. So this is not a restriction in the sense that every non-expanding horizon can be made into a weakly isolated horizon just by restricting the choice of null normals to a suitable class. Okay, is this clear? Yeah. On the other hand, the last notion was stronger. That is to say, we said that delta is an isolated horizon if in addition to if it is a weakly isolated horizon together with, or is a non-expanding horizon if you like, together with choice of null normal. Again, the equivalence relation is the same here. We just allow ourselves to rescale by a constant such that LDA minus LDA operating on any tangent vector equal to 0. Here it was 0 only acting on L, but it on any tangent vector. So if you like, I can even drop this and I can just say that L commutes to the derivative, intrinsic derivative operator on the horizon. And as I told you last time, that this in fact is a stronger requirement. In other words, it is not true that every non-expanding horizon can be made into an isolated horizon. It is not true that if I give you a non-expanding horizon, you'd always be able to find a clever non-normal which actually, with respect to which the full derivative operator is time independent. So this is a stronger, yet stronger notion of equilibrium. This is not always satisfied if you have non-expanding horizon. This is a genuine restriction on the geometry, on the metric and the derivative operator of the non-expanding horizon. And as I told you last time, for fundamental physics purposes, we really can just live with the weakly isolated horizons. We do not need isolated horizons, but for numerical relativity, the simulations always produce isolated horizons, and that is why this notion was introduced. Okay, this is where we were. Are there any questions? Okay. Yeah.
What's the difference between the third and the second condition?
This is true only for one vector field which is tangential to the horizon, which is the L vector field, and this is T, not L.
Okay.
So T is any vector field, any tangent vector field. This any tangent vector field. So we were successfully strong notion of equilibrium, and as I was telling you that there's interplay between geometry and physics, and now we're going to see a little bit more about this interplay between geometry and physics. So to see this little more interplay, what we need to do is to understand what restrictions on curvature. And from now on, before I do that, I just want to make one remark. So if you look at Schwarzschild spacetime, so full Schwarzschild classical picture, where I got this picture up here, where I got sky plus, sky minus. And these are the horizons, these are the event horizons. But this event horizon is also an isolated horizon. Every killing horizon is an isolated horizon, so we'll discuss that in a minute. But clearly there is a difference between this and this one. This is the black hole horizon, and this is the white hole horizon. So what is the difference? Well, the difference is the following. Here, this L that we're talking about it here, this L is always assumed to be, we assume this, use always L to be future directed. We don't say it explicitly, but that is assumed that the null vectors we're talking about are future directed. So this L is future directed. And so here we got L, which is future directed, and here we got L, which is future directed. So both of them are isolated horizons, they're killing horizons. And this L here is future directed, L here will be future directed, this null normal is future directed. But now if I look at the other null normal, which is also future directed, so this will be L here and this will be N here. And here if I look at the future directed null normal, it will be pointing like that. So the expansion of these null normals is 0. That is what we are told us. So this is not expanding. But the expansion of the other null normal for the black hole, if I take a two surface here and if I go inside, the area of these two surfaces decreases. So therefore, in the black hole type horizon, so black hole type horizons, theta sub n is less than 0 on the horizon. And for white hole type horizon, this is our tangent to the horizon, and this is the other null normal. So the other null normal has a property that theta sub n is bigger than 0. The area, you're going in an asymptotic region, so the area is, the light fronts are expanding in this up here. So on delta, white hole type horizons. The other future directed null normal. So L is one already null normal. You choose any cross section and you look at the future directed null normal. Then the statement black hole type horizon would say that theta sub n is less than 0 and this is bigger than 0 on delta for black hole type. So these are called, if this condition is satisfied, these are called future non-expanding horizons, and these are called past non-expanding horizons. I just say it because implicitly we're going to assume that we're only talking about the future non-expanding horizons, future weakly isolated horizons, future isolated horizons, but I would not say it explicitly every time just to avoid repetition. But most of the results we're talking about will be valid both for the future and the past for both these horizons. But for applications, we'll be restricting ourselves to the other. The expansion of one non-normal is 0, and the expansion of the other future directed non-normal is negative. That's what we're going to be looking at. Okay. So now, with this remark, we can now continue, and the statement is now what is happening to curvature, space-time curvature. At the horizon delta. And what we are going to look at is really restrict ourselves. We know what is happening to the Ricci curvature. The Ricci curvature is all completely given by whatever is happening with the stress energy tensor. We know that there is no flux of stress energy in that direction. So Ricci curvature also satisfies the condition RABLB is equal to 0. But then the question is, well, is there anything else as far as the wild curvature is 0? So we're looking at here the wild curvature. So again, I just remind you that some time ago, we saw that the Riemann tensor in 4 dimensions has 20 components. 10 of them are in the Ricci tensor, and 10 of them are in the wild curvature. And we're looking at now the wild curvature up here. So now, it is convenient, it's not necessary at all, but it's convenient to introduce a null tetrad and look at the components of this wild curvature in terms of the Newman-Penrose null tetrads. And this is something that I discussed a little bit before when we did Kerr-Shield solutions. So let us do that. So here we already have a null normal. So what do we have? So given a weakly isolated horizon, what do we have is this null normal LA where L tilde A is equal to C times LA. If L and L tilde are in this equivalence class L, then they are just only freedom that we have is that of rescaling by constant. We don't have absolute norm. We cannot say it's unit because it's a null vector, so we got this rescaling freedom up here. So given a weakly isolated horizon with a null normal up here, we would like to introduce a null tetrad. And I told you last time, I think, what the null tetrad means. It means we need to, so the Newman-Penrose type of null tetrad. So it is going to be 2 real null vectors, future pointing, and 2 space-like vectors, which are made into complex null vectors. So we need to have now an A. So we can choose one of these LA. We need to have LA, MA, and M bar. So basically, we got this isolated horizon, which can look like that. This is not a causal diagram, it's just a space-time diagram up here. So our L is like that. There's a freedom of constant rescaling, but it's a minor freedom, and we will talk about what happens under changing that freedom. And then the statement is that you can give me a cross section. There's no natural cross section. So you give me a family of cross sections, which is lead dragged by LA. So we can just choose an affine parameter, LA grade V or LA DAV, same thing, because we're just talking about this manifold, delta is equal to 1. So we get this affine parameterization. So this is V equal to V0, this will be V equal to V1, and so on. We got this affine parameterization here. So this is arbitrary. So the first section you choose arbitrarily, and then I call it V equal to V0, and then you just look at V equal to constant. You could have chosen this section and call it V equal to V0, and then you would have got another foliation. So at the moment, we just choose one, and then we just stick with it for a minute. If I did that, then I immediately have a null normal, another null normal, and so then NA is the other feature directed null normal. Such that L dot N is equal to -1 or -2 depending on conventions. The different places people use different conventions. For the Newman-Penrose, it is -1. So we choose that, and then we want to choose MA and M bar A, and these are just tangent vectors, complex tangent vectors to these surfaces up here. So in Minkowski space, so we choose MA, we get the numerical factors correct. In Minkowski space, we get MA, to be equal to well, let me just write down. So in Minkowski space, we set MA to be equal to R upon square root of 2 times grad A theta plus I sine theta grad A phi. And M bar A is of course complicated conjugate, and therefore we'll just change the sign up here. So if I wanted M bar, I'll put a minus sign up here. And now the point up here is that this in Minkowski space, you can see this is real and this is real. We just take a complex conjugation, complex combination, such that MA itself is null. Because if I take the norm of MA, this norm will be 1, and then this norm will also be 1, but because of minus I here, I will get I'll just get the difference between the two, and therefore I'll just get 0. So MA equals 0, and MA bar equal to 1. So our M vectors are such that M and this is satisfied, so this is in general the Newman-Penrose null tetrad. These are complex vectors such that their M bar is equal to 1, M is equal to 0, M bar of course is 0 because you just take the complex conjugation, and then LA equal to -1, LA equal to 0, and LA equal to 0. And it's also true that NA equal to 0, and NA equal to 0. So basically, all the scalar products, all the inner products between these 4 vectors, L and M bar are 0, except M bar is equal to 1, and Ln is equal to -1. Everything else is 0. And that is called a null tetrad. So this is just a convention to use. We could have just used d by grad theta and grad phi here. It is just a convention to use the complex linear combinations to make them null. Please.
Yeah, could you explain how you get M?
M. Okay. So thank you. So I've given isolar horizon, and I choose one cross section. So this is arbitrary at the moment. I choose this one cross section, and then if you give me any 2 sphere or any tangent space, 2-dimensional tangent space in any space time, then there is always exactly 2 null directions which are orthogonal to it. So that's a fact about just Lorentzian geometry. So given any two space like 2 flat, so for example, the space like 2 flat may be xy flat, right? D by dx and d by dy flat. Then the 2 null directions are just t plus d by dz and t minus d by dz. So given any space like 2 flat, 2-dimensional tangent subspace of the tangent space, there are always exactly 2 null directions. So we already have L, and therefore I just choose the other direction, and I just choose the normalization of M by just asking that this be equal to -1. Any other question? Okay. So this is the Newman-Penrose framework in which you just choose this tetrad in this particular way. It's convenient. It's actually is motivated, it's much more natural and simple in terms of spinners, SL2C spinners, where you see algebraic is kind of common sense that we should be doing this, but we're not doing spinners, and therefore it might look a bit strange to do all this construction, but they really come from SL2C spinners. All right. So now we take the wild tensor, and if you give me such a tetrad, so notice that here what is given to us is only L. N and M bar is our construction, right? There is freedom, because I could have chosen another cross section, then I will get another notion of N, another notion of M, and another notion of M bar. So it depends on the first cross section that you choose, so there is freedom there. So we have to keep track of this freedom, which we will in a minute. But at the moment, let's suppose that we are given we make one such choice. Then the statement is that the wild tensor can be decomposed into various parts, and the various parts are the following. First of all, we got these are all complex components. So the wild tensor has 10 components. So it has various algebraic symmetries, and therefore only 5 complex components are independent, non-zero independent. And so the first is called psi 0, and that is just given by C, A, B, C, D. Again, in spinners language, anybody who wants to learn about SL2C spinners, you don't have to remember any of these things. So, there are only 2 spinners, iota and omicron, because of 2-dimensional space, and psi 0 is just the wild spinner times omicron, 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 omicron. The next one is omicron, 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 iota. The next one is omicron, iota, 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 and so on. So it's very simple, but in the terms of tensors, it's sort of something that at least I can't remember. I always have to look up. So this is psi 0 is given by LA, MB, LC, MD. Then we got psi 1 equal to CAB, CD. I do it write it once because we're going to use it a couple of times, several times actually in the course. MB, C, D. So here I got 2 L's and then space like mass. Now we start peeling one of the M's and replace it by the other null vector, a real null vector, and we keep getting more and more N's as we go along. And so psi 2 is equal to CAB, CD times LA, MD, M bar, C, and D. So here I got 2 L's, here I got 2 L's, now I only have 1 L, and here there are no N, now I got 1 N, I got another N. But you can also, using the algebraic symmetries of the wild tensor, you can split into real and imaginary parts in a very nice way, and then that is just equal to 1/2 of CABCD times LANB, LCND plus pi by 2. So this is the real part, psi 2, plus pi by 2, or plus, this is the imaginary part is just plus 1/2 CABCD times LANB. This is the imaginary part, psi 2. How do you see that this is real and this is imaginary? Well, the wild tensor, of course, is real because the space-time metric was real. The only imaginary things come because we got M's, which are complex up here. And here we just have ln, they're all real, so this is real. Here I got real, but I got MM bar, and that is Q-symmetrized. And anytime MM bar is Q-symmetrized, you can just check from here, you will get I times the 2-dimensional epsilon tensor, and so therefore this Q-symmetrized MM bar is purely imaginary, and symmetrized MM bar is purely real. Let me just write down here, MM bar B, Q-symmetrized, this is purely imaginary. So you can just check in Minkowski space that that is the case. This is always purely imaginary, and MA M bar B, that is purely real. And this is in fact, this quantity is in fact the 2-dimensional metric SAB that we talked about, and this quantity is in fact I upon 2 times epsilon AB. the two-dimensional epsilon AB, the two sphere, the alternating tensor of the two sphere. So this is imaginary, this is real, and we got this. For the moment, we're not going to use this, but when we do scry, we'll need this. So let me just write down what is psi 3 and psi 4, just for the record here. So this is going to CAD, CD. So now, here we had one L and one N, and now we're going to get more N's up here. So I'm going to get here psi 3 is equal to LA and B. So it is like LA and B here that we had, LA in both these parts, so I've got LA and B times M bar C and D psi 4. So now I got two N's here. Here also I got two N's. Here I got one L. Now L has disappeared. So here I got two L's, and as you go down, L disappears and it's replaced by two N's. So it sort of goes from L to N. And these are not going to be necessary at the moment. These two are not going to be necessary at the moment, but we're going to live with this. Now, it is not very difficult to show. Yeah.
L and N are still defined as we used to do it before, like in the non-expanding horizons.
Yeah.
So you said these ones are for scry, but N was the one that goes into the.
I don't know, but I mean, they're really useful in scry. So these are the definitions.
It's really.
At the moment, these are just definitions, right? So L is supposed to be the tangential to the non-expanding horizon, and then this is what we got. When you go to scry, N is going to be tangential to scry. But I think these are the definitions that we're going to use later on. Okay, so these are 5 components. I know when you first see it, I'll say, why is everybody doing it? But the literature is completely full of this. When you see, for example, the curve metric, you never see what the wild tensor is. You only see psi 4, psi 3, psi 2. When people talk about numerical relativity, what are you where is gravitational radiation? They will say psi 4. So it's just better for you to know how these are constructed. These are very simple definition, and this is how it is constructed. Given any L, given any null surface with normal L, then there is some freedom in choosing N and M bar. But if you have fixed a cross section, then we got this choices given to us, and then we do it. So there's some freedom here, and then of course we have to worry about what happens if we change, right? Keep L the same, but supposing I choose another cross section, so N is going to be different. So N is going to be some linear combination of the old L, M, N, and bar, and so what happens and so on. So that's what we want to see. But one of the consequences, which I'm not showing up in class, I mean, it will take a lecture to actually prove this. It's not long, but you have to compute derivatives and calculate curvature tensor as usual. Maybe not a lecture, but half a lecture at least to do that. But it's a fact. So properties of a weakly isolated horizon, they are that we got psi 0 is identically 0, psi 1 is identically 0. So just because of this problem, again, this is not something that you would have expected. Actually, these are properties even of not only of but even of the non-expanding horizons. So therefore also weakly isolated horizons. But really, I mean, we started with something which looks so innocuous, but the statement is that coupled with field equations with the energy condition, it really has a very strong conditions, because one is saying that things are not changing as you go along L. What things are not changing? Well, the two-dimensional metric is not changing, and the one form omega that we have is not changing in time. And so these time-independent notions, I mean, they actually give you extra conditions. At the moment, let me just assume that I'm doing weakly isolated horizon, because many of these conditions don't depend on that. But in a while, what I do does depend on the fact that we've got a weakly isolated horizon. We have chosen L such that omega is time independent. So let me just say that not distinguish between the two. So this equal to 0 and this equal to 0. Now, so this is a fact, I'm just telling you, not proving it. And this is not something that is anything put by hand. You just use a definition, you calculate these quantities, and you show that these quantities are 0. It's not very profound up here. So, and they're 0 because, precisely because the 2 metric and omega are not changing in time. The second thing that follows is that this is true with, this is just a fact about Newman-Penrose tetrad, does not have to do with isolated horizons or weakly isolated horizons, that if in fact psi 0 and psi 1 are 0, then in fact psi 2 is gauge invariant. So let me just start from beginning. Let me go backtrack and let me explain. So in general, so let me, if psi 0 and psi 1 vanish, then psi 2 is one says gauge invariant, i.e. independent of the way the tetrad is completed. Starting from LA. Where LA here up here is really non-normal up to constant scalings. Actually, in general, if in fact, if given size, given LA, if you give me LA, not only equivalence class, but LA, then psi 0 is gauge invariant. It's not obvious, it's true. If psi 0 equal to 0, then psi 1 is gauge invariant. Each of these assertions is a straightforward calculation, not necessarily two line. It will take 10 minutes to prove it, but it is true. And then if psi 0 equal to 0 and psi 1 equal to 0, then psi 2 is gauge invariant. And it goes on like that. So the point is that if this, basically what one is saying is that if I change this tetrad, then psi 1 acquires a piece of psi 0, psi 2 acquires a piece of psi 1 and psi 0. But if those quantities are all 0, then psi 2 is itself invariant. You can see trivially here that if I rescale L by constant to get L tilde, then to have this condition, N tilde will be 1 upon that constant. Therefore, N times N will be invariant. And that is why this does not change under rescaling of L. And this does not change under rescaling of L. And so therefore, this actually does not depend on L, a specific normal, but only on L up to normalization factor. So these are gauge invariant quantities, and this is important. Now, why is this important? It is important because, in fact, what it is telling us is that we should be able to extract physics from psi 2. Again, this is this beautiful interplay between physics and geometry. We introduce physics in order to impose some conditions of geometry. Now the geometry tells us that the gauge invariant quantity constructed from curvature is really the psi 2. And therefore you would expect, oh, that means physically I should be able to use psi 2 to construct some physical attributes of the horizon. That is indeed the case, and that is what we are going to see just now. In particular, it turns out that so I'm just telling you these facts, and the third fact is that if I take we have this rotational, this one form which we call rotational one form, omega A. If I take its exterior derivative, that is just equal to imaginary part of psi 2 times, this is the two-dimensional epsilon, so this is equal to I times 2I times MA MRP. Okay. So the statement is that dA of omega b is just given by that up here, and then it follows immediately, or you can say that epsilon AB and dA omega b. I can take epsilon on the other side, epsilon on the other side. This is just equal to imaginary part of psi 2. Now, why is this interesting? Why is this important? Well, this is important and interesting because it turns out that omega, we already called it the rotation potential, as omega has an information about angular momentum. So, if omega equal to 0, implies no angular momentum. I should put it this way. Because what is, or more precisely, if imaginary part of psi 2 is equal to 0, then we'll see that there is no angular momentum. So therefore, this is what I call the rotation coefficient, rotation potential, one form, rotation, one form. So what we have seen is the following. We started some mathematical definition of non-expanding horizons to talk about horizons which are in equilibrium. Again, these quasi-local horizons are obtained by just stacking on the top of each other marginally trapped surfaces. So it's really a marginally trapped tube that we got. It is null, and we're looking at the weakly accelerated horizons. And the statement is that for weakly accelerated horizons, this is particularly true. And then in general, more generally, so 4. So this imaginary part of psi 2, therefore, has information about angular momentum, and the real part of psi 2 has information about mass. And because of these isolar horizon conditions, psi 0 is equal to 0, psi 1 equal to 0, and furthermore, it turns out that this psi 2 is in fact not only gauge invariant, but is time independent. I.e., on a weakly accelerated horizon, what we have is a weakly accelerated horizon is in equilibrium. We discovered this in a stronger sense than what we put in, that both real and imaginary part of psi 2 are time independent. And the last remark is the following, it just follows from here. If I put this L is mm bar, so it is really the epsilon on these two-dimensional spheres that I got up here. But if I contract with this L, then L of course is going to kill m and m bar, because LA MA is equal to 0. That's going to kill this mm bar. So because LA epsilon AB equal to 0, that implies that twice LA dA omega b equal to 0. But we're going to Carta it. You can expand this out. Maybe I should do it in a minute. This, okay, let's do it, expand it out in a minute explicitly. So this will tell you that LA dA of omega b plus LA dB of omega a equal to 0. But I just expanded out. I didn't do it. Minus equal to 0. I didn't do anything up here. And now I take this inside. And I know that omega is orthogonal to L. So L goes inside. Therefore, I'm going to get here. This is all on the horizon. Intrinsic We're not, in these equations, we're never heard of the rest of the space-time. We're just looking at properties of horizon. So therefore I can take this inside, so I get here LA dA omega B minus dA LA omega A. But I have to correct, because I took this L inside, so I get here LA omega A times, sorry. So I get here, I take inside, and I get here omega A times dB of LA equal to 0. Okay. So I take inside and I get this. I just said something incorrect. I think I said that I take inside 0 is not 0, it's just LA omega A. This is just equal to the surface gravity kappa. Kappa was just defined to be, so remember kappa was defined to be equal to LA. Kappa was defined by LA dot A LB or LA LB equal to kappa LB to solve surface gravity. So this is just equal to LA omega A LB equal to kappa times LB. So that tells us that kappa is equal to LA omega A. So this is just equal to kappa up here. But these two terms together combine LA dA omega plus omega dEl. This is exactly L. So this term and this term is just L of omega B plus or minus dA of kappa equal to 0. So this is the equation that we get. So what I've done is I use a Cartan identity, which is that LA twice LA dA of omega B, L times exterior derivative is just equal to L of omega B minus dA of L of omega. This is the Cartan identity, that's what I've used. I've explicitly proved it here, that's what we have used up here. And what we're saying is that on a weakly isolated horizon, this is equal to 0. This is equal to 0. Therefore, it follows that dA kappa equal to 0. So previously I always denoted kappa by kappa sub L to make sure that what it refers to is L. So what we find is that kappa L is constant on a weakly isolated horizon. This is often called the zeroth law of black hole mechanics. See, it's completely non-trivial, because kappa, I told you, is like the surface gravity, right? The surface gravity. It's like little g on the surface of Earth. You all know that little g is not constant on the surface of Earth. If it was perfectly spherical, it will be constant. But it's not perfectly spherical, and therefore, now if I take a curved horizon, for example, then the horizon is not spherical. So there is no reason why surface gravity should have been constant. But because the horizon is a killing horizon, in particular, it is a weakly isolated horizon. So we see here several things. One is that we really did not care about the fact that it was a horizon. You know, it came from sky, and passed up sky, etc. That played no role in this result. In fact, even killing horizon did not play a role in this result. What played a role is just that it is a weakly isolated horizon. It's a very small thing. We did not need a global killing vector at all. We just need what is happening on the horizon itself. That the horizon be weakly isolated, then we see that kappa is the surface gravity is in fact constant. So you can have black holes. In fact, in a minute we're going to see that. We can also have black holes which are distorted. They're not like Kerr at all. The horizon is very distorted, has a lot of structure in it. And even for those black holes, it is true that the kappa is always constant. And that is the zeroth law, and this idea. And this just follows from general relativity. I did not use anything else other than general relativity. Neither quantum mechanics nor statistical mechanics, anything. Just general relativity. And then the statement is that, I use the energy condition, but apart from that, I did not use anything else. The statement is that this kappa is always constant, and then as you probably know, h bar times kappa has the dimensions of temperature, and in fact is identified as the temperature of the horizon as seen from infinity. And what we are saying is that the horizon is in equilibrium if its temperature is constant, and we find here that indeed kappa is constant. So there are all these notions of equilibrium of the horizon, that many quantities are time independent, and all those issues, all those notions actually can be derived, though the physically interesting ones can be derived just by assuming that it's a weakly isolated horizon. Last remark, and then I'll take questions, because then we'll go to the next topic. The last remark is that psi 0, psi is equal to 0, psi 1 equal to 0, psi 2 is gauge invariant, and it's time independent. These quantities are not gauge invariant. In other words, they depend on the choice of tetrars that I've chosen. In other words, if I choose the tetrars differently, then psi 3 will pick up a little bit of psi 2, psi 4 will pick up a little bit of psi 3, and psi 2. Okay, so they get reshuffled, okay, from each other. You know. And these quantities are not 0. And furthermore, these quantities don't even have to be time independent. We don't know that they're time independent on an isolated horizon. If it were a killing horizon, then along the killing trajectories, the full 4-dimensional geometry is time independent. And therefore, everything that you write down that is constructed from geometry would be lead dragged by the killing vector field. It will be constant, it will be time independent on the horizon. Constant in time, not necessarily constant in angles, but constant in time. But for the weakly isolated horizon, only psi 2, these are 0, and psi 2 is time independent, but we don't really have any control on this thing. And the interesting thing is that for laws of black hole mechanics, for black hole thermodynamics, it is irrelevant. So that's why this isolated horizon framework, or the weakly isolated horizon framework, brings to forefront the properties that are essential for black hole thermodynamics and removes the excess baggage. I was going to say excess garbage, I didn't mean that, I mean excess baggage that we do not really need in order to prove, in order to establish the thermodynamic properties of black holes. Okay, any questions? We're done with this topic.
All the statements you said were correct at the horizon, right? Like, right, we're talking at the horizon.
At the horizon. We're
Yes.
talking about at the horizon. Everything here is on delta. I mean, these quantities, because if I go away from delta, I don't know what L is. On delta, I know what L is. Yeah.
I think in the proof you used the fact that psi 2 is non-zero, right? To show that the zero flaw of black hole mechanics works. For part 5, I think.
Part 5. Yeah. So the statement is that if psi 2 is 0, then grade omega itself is 0.
Yeah.
And I can put L in it if I wanted, and I'll get the same thing.
Okay.
So I did the non-trivial case, but you're right. For it. Otherwise, I don't need to. If you imagine part of psi 2 is equal to 0, then the same proof works. It's just that. Okay.
The long issue 5, is LA epsilon be equal to 0? This depends on what?
LA of what? Say it again.
LA epsilon may be equal to 0?
Oh, LA of epsilon may be equal to 0. Is just the LA times epsilon may be equal to 0. This epsilon is just the mm bar. It's a 2-dimensional epsilon. I mean, in an invariant manner, the statement is that I got a null surface and I got a metric QAB. The metric is actually lead dragged by this. Therefore, you can go to the base space, which is the space of orbits on this L. I get a 2-sphere, and metric really lives there and is just pulled back here from the base space. Right? If I have a 2-sphere, each point up here is an entire integral curve of LA up here. So there's a 2-sphere on which it exists. So the metric QAB, let me call it Q bar AB because it lives on S2, and epsilon bar AB, they live on this S2. And the epsilon AB and QAB here are just pulled back up there. So because they are just pulled back, they're killed by the normal direction up here. Or in terms of basis vectors, epsilon is just given by MA bar B, and L is perpendicular to M, and it is perpendicular to M bar because of null tetrad, therefore epsilon. Yes.
If I would like to use this planar length, but it is a gauge freedom that you are speaking about. What kind
That is the freedom in choosing. So what we have is,
of
this gives you an omicron,
full SL2C
that
or
SL2C,
subgroup?
SL2C.
So the gauge choice here, that is the way in which I complete those.
Right. So you are given omicron, because L is like omicron. But iota can be chosen because I can add to iota a multiple of omicron. And so, sorry, I can add to iota multiple omicron. So iota is arbitrary, and that is what makes us. So psi1 will pick up a little bit of psi0 and so on. Yeah, let's talk about spinors later because the rest of the class is not to get to spinors. I just wanted to say that I have a meeting at 12:15, so if you can come before that's fine, otherwise after 1:30. Yeah, because I missed my office hours also because I have to be in this panel on Friday. Okay. So. We now do the last topic, and the last topic is multiple morphings. Now you see, I was asked repeatedly, when I talk about weakly isolated horizon, I'm not talking about the global structure. I don't know what space-time is outside. Space-time just admits this weakly isolated horizon. So it does not have to be a vacuum space-time outside. So for example, if I got a static black hole, non-rotating isolated horizon or weakly isolated horizon, it doesn't have to be Schwarzschild outside. Because I may have, for example, a matter ring. Okay, so the weakly isolated horizon considerations are all local to that. First of all, we never talked about event horizon. I don't know if this is even a scry, right? I mean, and secondly, unlike Killing horizon, for the Killing vector field, it is globally well defined, right? The whole space-time is stationary. I don't need space-time to be stationary. I don't need the space-time to be vacuum either. So all these weakly isolated horizon considerations are local to delta, hence outside one may have a matter field, so there may be matter field outside, and then uniqueness theorem is violated. Now, astrophysically important matter fields might be magnetic fields or accretion disk. And the Jena group has done a lot of exact solutions of stationary black holes with the horizons, even asymptotically flat, but with accretion disk there, outside there. So such solutions exist. They are widely believed to be not stable because matter will fall from the disk into the black hole and so on. They would not remain stationary under perturbation. But the solution exists. So because of this, the solution need not be curved. And the second thing is that even if it is vacuum, the solution need not be stationary. We did not ask for a global Killing field at all. Now, so when the black holes collide, they merge, and they settle down, and the numerical simulations show that in fact they settle down so that at late times it looks like a curved black hole. Well, what does it mean it looks like a curved black hole? Well, curved black hole has no radiation. It's stationary globally. So of course it cannot look like a curved black hole because there's radiation going out. That's what LIGO is. Right? So the only meaning we can give to it looks like a curved black hole is that the near horizon geometry is that of curved black hole. But what does near horizon geometry mean? To what approximation, etc.? The simplest way to make it concrete is to say that the horizon geometry is that of curve. The horizon geometry itself is that of curve. But outside it is not curve at all. And that is why these isolated horizons are very important, because that is what is really one sees in numerical simulations. One does not see killing horizons in numerical simulations, and one does not see event horizons in numerical simulations when the simulations are first performed. Once they are completed, you can trace back the horizon, and as we said before, the horizon is not teleological. It has properties that are physically unsettled. But the weakly isolated horizons, on the other hand, are completely local. So in fact, let's already emphasize it, that solution need not be curved. Or in the static case, the solution need not be spherically symmetric and therefore need not be and therefore not Schwarzschild. And in fact, an infinite family of such solutions has been known for a very long time. They are called Weyl solutions. And these are very well understood. It turns out that Weyl realized that in fact, even though Einstein's equations are non-linear, if you assume that the solution is static and axisymmetric, you can reformulate Einstein's equation so that your job is to solve only one linear equation. And once you have solved that linear equation, then by algebraic manipulations, you can get the entire solutions. And so you obtain a whole family of solutions which are called Weyl solutions. Much later, Garrosh and Hartle just took these Weyl solutions and looked for which of them have a regular horizon and which are asymptotically flat. So they are candidates for black hole with matter outside. Okay. With potentially matter outside. To make them asymptotically flat, you put some matter outside and make it asymptotically flat. So they looked at that in detail. And here, Steve Fairhurst and Badri Krishnan, when they were students, generalized that word while working on isolated horizons and showed that in fact there is also a family of vacuum Weyl solutions. In other words, black holes which are matter rings, but black holes which may have magnetic fields and electric fields and so on. And they also looked at distortions due to external magnetic fields. And the kind of external magnetic fields they needed, the magnitude, they needed about 10 to the 16, 10 to the 17 Gauss. And at the time I thought, wow, that's way too much, right? Because on Earth it's about 0.5 Gauss. And even for the supermassive black holes that people have seen, at first they thought it was going to be a lot, but only about 500 Gauss. But for these smaller black holes that people are doing numerical simulations formed by neutron stars, they're getting magnetic fields of the order of 10 to the 15, 10 to the 16 Gauss. So now these considerations of Badri Krishnan and Steve Fairhurst might become relevant even astrophysically. I'm not saying that everything is done and they are clearly relevant, but it's worth actually following through and see in the light of what we now know, how relevant they are, at what time that will actually make difference. So these black holes are not going to be just represented by curve. There will be some departures within a few percent. The question is it 1%, is it 10%, is it 5%? But these are significant things as LIGO increases its sensitivity. Okay, so therefore that's why looking at these black holes, looking at these weakly isolated horizons, which are more general than curve, is of great interest, not only in terms of structure of the theory, but also in terms of actual practical things for LIGO. Okay, so how do we characterize the geometry of the horizon? So what is the geometry? It's going to be L, QAB, and omega A. Okay. dA, and therefore omega A. Knowing dA and L, you already have omega A, is geometry of the weakly isolated horizon. The point is the following, again, physically the question is the following. Numerical evolutions start, they take two black holes. What do you mean by black holes? Well, they take two far away marginally trapped surfaces. And these marginally trapped surfaces, and then they evolve space-time. These marginally trapped surfaces are supposed to represent local black holes, right? At that instantaneous black holes. And these black holes then go around, and then finally they merge, and then they settle down. When they settle down, they're going to become a weakly isolated horizon. If it is curved, we know what that weakly isolated horizon should be. where multiple moments of that weakly isolated horizon, which we can actually calculate. There's no problems. So the question is, what it may not occur. There may be accretion disk. Again, these numerical simulations said that there is of the order of 10% of matter is an accretion disk outside the black hole. When the two neutron stars collide, that's what we heard in the seminars, about 10% of the matter is an accretion disk. And therefore, it's not going to be Kerr, it's going to be perturbed Kerr to the order of about 10%. So the question is, how much does the horizon geometry change? And can we have accurate enough simulations? We should be able to see this, that it is really not Kerr, but there is a departure from Kerr. How do you measure the departures from Kerr? The problem is that different numerical simulations are carried out in different coordinate systems. And in some coordinate system, the horizon looks like this. In other coordinate system, the horizon looks like that. But these are all coordinate depictions of the horizon. What you would like to know is an invariant characterization, which doesn't depend on this, which does not depend on this choice of coordinate systems. In other words, you might choose coordinate systems, but then I should be able to produce for you some invariants. So Shorab chooses a coordinate system. He finds something, and Shupeng chooses another coordinate system, and he finds something. And the question is, are they finding the same thing, same horizon or not? How do you see that? And this invariant characterization is coordinate invariant coordinate. Is provided by multiple moments. So these are just numbers, right? So we're going to define them next time because we only have 2 or 3 minutes left. So next time we'll define them. And the statement is that any numerical simulation can characterize this family of numbers. And there's a mathematical theorem which tells me that if they give me this family of numbers, I will be able to reconstruct for them the horizon, a weakly isolated horizon. And conversely, given a weakly isolated horizon, from there I can construct this family of numbers. So this family of numbers provide us a kind of a nice coordinate invariant characterization of the horizon geometry of these quantities that I will write up here. And then the statement is that can we, what are these numbers? How do we calculate it? I'm not going to prove for you these results because again, any proof will take at least a lecture or 2. So, but I'm going to tell you what the results are, going to motivate them, and then, there are references. If anybody is interested, well, you can look at these references. And these multiple moments, the idea is very similar to what happens in not statics, but electron magnetostatics, in other words, stationary currents situation. There we know that the fields are characterized by source multiple moments, and this is very similar to that. The source is a time-independent horizon, and therefore we can calculate its multiple moments, and that's what we'll do next time. Okay, thank you.